data space. And so we've had many conversations over the last few months about data science in the university, and I'm trying to convert people to be Bayesian. It's a sort of a religious fervour in the stats world. So anyway, so I was asked along for my sins to come and talk to you today, and I really want to talk to you a lot about what it is to be Bayesian, what it is to have reproducible research, which I know goes at the heart of a lot of the work or the research that you do. And to that end, to sort of try and talk to you about how Bayesian statistics can add to that. And so, and the title of the talk is "It's to P or not to P." Although I've got the funny cartoon with the cat, the P actually refers to using P values, so which I presume that Tina knows about. You know about P values, so I think I'm okay there. All right. So what I'm going to do is start off by saying, let's think probabilistically. It turns out, if you have a look at a lot of research done on human beings, we are not intuitive statisticians. Thinking probabilistically comes really hard to us, and I've got a few things up here. One of them is the Sally Clark case, another one is the Space Shuttle Challenger, and the last one is the book of what the most successful people to do before breakfast. And I'm going to use them as motivating examples about why you need to think carefully about Bayesian statistics. So just to sort of run them through really quickly about what this was. Sally Clark was a woman in the UK. She had 2 children who died of SIDS, and she was convicted and put in jail. The quote, the figure that sank her was this 1 in 73 million, that they said that it was a 1 in 73 million, that it couldn't happen by chance or adventure, or she was guilty and she was sent to jail. The second one is the Space Shuttle Challenger. You're all probably too young to remember this, but there was back in 1986 or 87, a space shuttle was sent up. There was a controversy at the time, which was whether or not the temperature was going to be about 30 degrees Fahrenheit. They'd had failures in the past, and they wanted to know whether the failures, this was number of breaks on the O-ring, which are parts of a rocket. I don't really know much about rockets, but I do know that you need to have 0 O-ring failures if you're to make it into outer space. And these are the number of breaks they had versus temperature. And they were trying to say, well, is there any relationship between temperature and whether or not this shuttle is going to explode? And that's the data that they had. In the end, they sent it up and it did explode. Lastly, I just want to talk about this book. This is just an example of many books that you will find on airport shelves. You know, they are always about what successful people do. It's about somebody who interviews successful people. And in this particular book, I thought this was nice because it says this is what people do before breakfast, and you're all here today, so I want you to feel particularly successful because you're here today. But actually, it's fundamentally flawed as a research bit. So, okay, so Bayes theory. I promised him not much. So, but you cannot really do a talk on Bayesian stuff without Bayes theory. So all this says is that these are events, A and B, probability of A. This vertical line here means given or conditional. Given that B occurs, is related to the reverse condition, which is the probability of B given A by this formula. It's called Bayes theory because there was a fellow, Thomas Bayes, about 1780, who came up with this. Actually, though, it was a great piece of, what's the word? The English went down in history as inventing Bayes theory, but really Bayes only came out with that one thing, and there was a fellow who was a Frenchman in class who really should be called Laplace's theory, because all the theory around probability that got developed was by this Frenchman Laplace, and the British not being ones who will never lose an opportunity to take something from the French. Actually, you call it Bayes theory. Okay, but basically, people are really not good at doing this switch mentally. They're really difficult. Okay, so we're now going to walk through a really quick example about, and I'm going to ask you questions. So get your thinking caps on. Okay, so I've got here an example which is about in your world. In your world, I mean the medical world. So you would often have, when you're having a look at tests for things, you get a group of people whose disease status is known, and you see how well the test differentiates for those disease status known people. So, for example, there is a test. Okay, so 100% of patients. So if you have HIV, you will test positive with probability 1, right? 100% of all patients that have HIV tested positive. 98% of people without HIV tested negative. Okay? about 0.1% of the population at that point in time had HIV, right, for that particular group. Now, of course, we've got here are some facts. You're feeling unwell, you have a test for HIV, and it returns a positive result. What is the probability that you actually have HIV? So I'd like you to think about that, and I'm going to ask for a show of hands. I'm going to sort of, if I don't get a show of hands, I have to pick on people. So really, it's better to volunteer. Okay, so just have a think about it. Think about what's the probability you've got this test, what's the probability you've got HIV? So maybe I'll just have a show of hands that says, do you think it's above 90%? Right, do you think it's between 80 and 90? 70 and 80? 50 and 80? Okay. Between 30 and 50%? Between 20 and 30%? Between 20 and 10? Under 10? Let's see. Okay, we're just going to define a few events here. A is the event that the person has HIV. So we're just going to set it up as a maths problem, right? B is the event that the person tests positive. So what we want, so you've tested positive, right? So given B has occurred, we want the probability that you actually have it, right? So what sort of information are we given? The first one says 100% of people with HIV test positive, right? So that means, given A, we know that they have HIV, the probability that they test positive is 100%. So that's this bit here, right? It's not this bit over here. 98% of people without HIV test negative, and I've just used a little sort of notation here. A B with a bar or an A with a bar across the top just means the reverse of it doesn't happen. So A bar means people don't have AIDS. So this is the people without AIDS, and not B happens. So in other words, people without AIDS tested negative. That's 98%. That means that people without AIDS tested positive 2% of the time. And now you can see why this thing is going to be quite surprisingly low, right? Okay, 1% of the population has AIDS, that's P of A, so all we're really missing is this P of A, P of B, right? So P of B is people who test positive. Well, people who test positive, they either test positive and they've got AIDS, or they test positive and they haven't got AIDS. So about 2%, a little more than 2% of the population test positive. Now, what do you say about that? What percent of the population actually have AIDS? 1%, 0.1%. We've got 2% testing positive. In other words, 20 times more people testing positive than actually exist in the population. So it shouldn't be surprising to you to learn that the probability that you actually have HIV, given that you've got a positive result, is less than 5%. Now, the reason I do this is, unless you sort of systematically train yourself to think this way, it's really difficult. It is incredibly difficult to think this way in your head. And it's only people who've really seen these sorts of problems before and have this mechanism in their brain. Oh, okay, that's that sort of problem, and now I've got to think about it like this. Without those formal training of thinking, it's very difficult to do. Okay, so let's go back to our 3 issues before we talk too much about p-values. We've got the Sally Clark's Space Shuttle Challenger and the book, right? What the successful people. Let's take the book first. Now, do you think you should get up in the morning and start doing things before breakfast? I mean, what is this book really about? So let's define events. This book is about successful people, right? They have only interviewed successful people. And it's about their schedules. So if I'm thinking about it, it's about, given that you're successful, what does your schedule look like, right? Every person that they've interviewed in this book is successful. Is that really the quantity of interest? What do you want to know? You're sitting here, you want to know, I want to know. I like to be successful, right? So I like to be successful. What do I have to do to be successful? So I want to be able to figure out, does having a schedule like that lead to success, right? And what we've just seen is that's a very different probability from success, what your schedule looks like given that you're successful. So it's the wrong conditional probability. And in fact, hopefully by now you will say every time you see in an airport shelf books about what 10 successful people did, you will say that's sampling on the dependent variable, it's rubbish. And you'll move past. Okay, so Sally Clark's a slightly trickier one. What does this 1 in 73 million mean? Actually, the 1 in 73 is wrong also, but that's another story. Basically, it's a prior, B is the event of 2 deaths. It's a prior probability. It's the probability that I randomly select somebody that could be in this room, somebody down the street in Australia, in Sydney, and they've had 2 deaths, right? So that's it's a terrible, shocking thing, but that's not what's happened here. We've actually observed those 2 deaths. We don't want a prior probability. This person is here because they have been that 1 in 73 million. The real question that we want to ask is not what's the probability of 2 deaths, but given that 2 deaths have occurred, what's the probability that they were murder versus what was the probability that they were since deaths? That is the correct probability. Turns out it's about 20%. And this was such an astonishing case that eventually the Journal of the Royal Statistical Society, the Royal Statistical Society in the UK, actually wrote to the law lords and actually had to point out this fallacy of logic and got a release. So it was a triumph of stats, actually. I wish it had a happy ending, but it didn't, because she had a 3rd child that was taken away from her while she was in jail, and then she ended up, unfortunately, drinking to death. So it was a very sad story, and probably not a great one for this morning. But the point here still remains that you can see how very smart people, the people who sit on these cases, are very smart, the judges and everything, but if you're not really trained to think properly like this, you can get it spectacularly wrong. And probably nowhere more spectacularly wrong than this one. Okay, what have we actually got here? They had a look at the they were saying, okay, they went and got the failures, the times that it had failed. And they had a look at the number of breaks in these O-rings. So what were they conditioning on? They were only looking at failures, and they were having a look at how temperature, given that you were failed, they had a look at what the distribution of the temperature was. Now, I'm going to ask, is that the question that you want to ask? Is that the probability you want? So the temperature that morning was forecast to be 30 degrees. What is the probability that you want? You want probability of this thing failing given temperature is 30 degrees. The flip of that probability, okay? To compute that, you need to know about the times when it actually succeeded. You can't compute the reverse of that until you actually observe the successes, the times that it succeeded. These were the successes, all down here, right? So these are 0 rings, all these launches here were successful. And if you look at this, what you'll see is that there was no successful launch below about 66, and there was no failure above 75. If you do something which some of you may be familiar with, like a multinomial logistic regression, or logistic regression, just turn it into a 0, 1 failed or not failed. With temperature as your x variable, the probability that it was going to fail was as close to 100% as you can get. And so this was another example of just a spectacular failure of logical things. So what do all these things have in common? Well, what they have in common is a failure of a logical and coherent probabilistic thinking. And it's not that these people are stupid. It's actually hard to think this way. And so you might be saying, well, okay, this is all very well, but what's this got to do with p-values? And so now I'm about to tell you what it's got to do with p-values. Okay, so 5 things this talk will discuss in the next 10 minutes. Okay, to be or not to be, that is the question. Okay, that's the first one. The other thing is, all models are wrong. Everything that you do when you model the world is wrong. Just some are really useful, okay? There's a big difference. Oops. There's a big difference between predicting, being able to predict something, and understanding the causal mechanisms. And I'm going to show you examples of that. Researcher degrees of freedom. There are many ways to cut the data, and I think that that's sort of relevant for the world that we live in now. And the last thing, you know, I'm a big believer in embracing uncertainty, okay? So being comfortable with it, being able to quantify it, and acknowledging that it exists. It's not about big data holds the key to the universe, okay? So that's what this talk is not about. Okay, what's conditional probability got to do with reproducible research? Well, I think it's a long bow. Let me first run through some of the statistics about reproducible research. You can see here what this one is quite, so these were randomly randomized clinical trials, 20 observational studies, only one replicated. Now, if those observational studies used a p-value of 0.05, how many of them would you expect to replicate? If there was nothing in them, how many of them would you expect to replicate? None. Sorry, if they were all there purely by chance, you were to do it again, how many would replicate it if there was no effect in any of them, right? And let's imagine a world where there are 2,000 studies done, and you get those top 20 who you get 20 that have found a result, but they're all rubbish. And then you redo those experiments. If you use a 0.05 significant level, you would expect one to replicate purely by chance, right? So, which is actually what they found. So this was rather alarming. So there's been lots of research that's done this. These were some really famous publications that were considered groundbreaking. A lot of them were failed to replicate. Oops. So what is it that's causing all this failure to have reproducible research? Well, how many of who here is an academic? Right, okay. So we all understand the behavioural part of this, which is we all know that you get published more if you actually have something to publish. There should be a journal of no findings, right? But there isn't, unfortunately, where we're lobbying hard. Actually, there are. They're called statistical journals. We never have to find anything. We actually know it's a lot of fun. We just get to do the methods part. But and you can see down here, you know, these were accentuate the positive. These are disciplines, and you can see that the percent of publications that appear that was produced positive one, over 90% for psychiatry and psychology. So, you know, it's astonishing. What are the explanations? Well, certainly in observational data, there are a lot of confounds, and I like this graph. What we have here is the Apple, the green line is the Apple's share price on the 1st of January for each one of these years. And the blue line is the number of people who were killed by dogs. This is in the US. Now, if you were to do a correlation coefficient on those, it would be minus 0.97. So they're almost perfectly, when one goes up, the other goes down. And so when I put this up as an example in the stats thing, I said, so you can see how you can get these spurious correlations. I mean, what on earth, you know, if you were managing director of Apple, what would what relevance does this have to have? And a student would understand and he said, oh, you'd have a policy about, ensuring dogs stayed on leashes. So there'd be no dog bites, and then the share price would go up. I thought, I must have been talking, I failed as a teacher. Because that's clearly not what happened. Okay, so the confounds, prevalent. Okay, so failure to account for model uncertainty. I'm going to talk a lot about that in the next 3 minutes. And the misuse and variability. So there's the person, doing his due diligence to the p-value. Okay, and the last one, but these two categories are related at any point along the way. You're going to be able to figure out which one you actually want to do. You can choose to do something to the data and cut the data, and then you can choose to use a frequentist, or you can choose to use Bayesian, and all the way you're actually working down the line at, well, significant yes, and they're giving each other a high five because that's the study that's going to be written up and submitted for publication, right? And so that's, you can do this at your leisure later. The answer is 3. I wrote that one down. So, but this was done by a stats professor. He asked a bunch of physicians, and half of them answered incorrectly. And it wasn't, the point was that, not that physicians don't know anything about stats, it's a p-value is a convoluted thing. It's a terrible thing. Because what is a p-value? Let's have a look at it. You've got a null hypothesis. What you do, let's get this clear how this p-value thing works. You've got a null, you've got a hypothesis. I think that this drug is going to cure this sort of cancer. I'm going to assume the reverse, right? I'm going to assume it's not going to happen. Then I'm going to collect some data and I'm going to take some function of the data, which I call a test statistic. Maybe it's a regression coefficient, maybe it's a sample mean, something like that. Conditional on the reverse being true of what I originally suspected. You can see how this is starting to get very convoluted, right? So, and that's what a p-value is, right? So that's why the answer was 3. But do you really want this? Do you really want to know what is the probability of some function of the data if the reverse of what you suspect is true is true? No. What you actually want to know is your hypothesis true. I've got some data conditional on the data. Is my hypothesis true? It's quite simple, really, isn't it? That's exactly, and that's what we do in Bayesian statistics, okay? So we call this thing a posteriori probability, and we directly compute that, not some artificial p-value. Okay, so this was stuff, this is a paper that we're about to submit to Nature Methods. It's called irreproducibility, nothing is more predictable. And it's done with my postdoc and Nick Boswell, who's at the Brain Institute. Okay, and we're looking at disengaged youth. It's a very important problem, and I'm sure people here are very aware of how important the problem it is. And so they have a data set that they looked at, and they tried to get what were the factors that might predict, whether or not somebody would be disengaged. So let's talk a little bit about the data set. The data set had 650 observations and 50 covariates. So 50 possible explanatory and 650. By today's standard, that is incredibly modest. That's a very, very modest data set, okay? As I've said, very modest in size. However, from this very modestly sized data set, you've got 50 covariates. You know, how many ways are there, if you want to select which variables are in or out, if we think of a string which consists of 1s and 0s, a 1 if a variable is in and a 0 if it's out, so it's a string that's 50 long, consisting of 1s and 0s, you know how many ways there are different permutations of that one string. Well, there's 2 to the 50. It's greater than the number of stars that are in the Milky Way. It's greater than the number of insects on the planet Earth. It's a very large number. And so when you want, and this is without interactions, so when you want to choose which one of those possible 2 to the 50 combinations, it's a very, very hard problem. And our point is, there's probably not one single model that is the right one, right? There's lots. Okay, so what did Nick do in his previous life before he became a Bayesian? Well, he did this. We took this data set, and what they do here, he said, oh, here is his top 20 things that he thinks affect disengagement, and then he ran a regression for each one with it individually, like a univariate regression. Is everybody familiar with regression? Yeah. Okay, and these are the p-values from univariate regression. So he said, okay, so these ones got low p-values, so I'm going to put them into a second stage. It's a 2-stage step, and then I run a multiple logistic regression, and these are the things that come out. This is actually a very standard technique. It's very ad hoc, fundamentally flawed, but this is actually very standard. So what did we do? So what? I did say that was only one. This is the only other slide. So this says, don't worry about that time. This says, I want to predict whether somebody is going to become disengaged or withdrawn based on all the data that I have. What happens in Friedman's world is you select a model, right? You select this model here that has age, sex, criminal, these things, and you predict based on your model that you've selected, right? What this says is, well, actually there's no one model that's right. There's actually 2 to the 50 of them. And I can do a prediction based on each one of those 2 to the 50. And I'm going to weight my prediction by how likely that particular configuration or those particular set of models is right. So it's called model averaging rather than model selection. And then we go, and so this gamma, I don't know why we call parameters Greek letters, but this gamma thing is this vector of zeros and ones, which, you know, a 1, 1, 1 would mean x1, x2, x3 are in the model, and if there's anything else with 0, so that's what this gamma is. So we make inference about which variables are in via this thing called gamma, which is the posterior distribution. Okay, now I've cut out obviously a lot of the result. I'll talk about the factor combinations in a minute, but just in that, these were factor combinations listed from highest posterior probability. So this was the most probable one. This was the 20 most probable one. Remember, this is 20 out of 2 to the 50, so this is still... now, are you familiar with this term called area under the curve? And you know that higher is better, right? Yeah. And it measures, you know, it measures how well you classify things, essentially. Now, this model is much more probable than this model, but if I run my eye down here, what you can see is that how probable a model is not really related to how well it predicts. Can you see that? You know, this one hasn't got the highest AUC. The highest AUCs are these ones down here, and I'll talk a bit about what they are. So, two key takeaways from this. Predictive ability is similar for models with entirely different factors, and it is unrelated to how likely that model is if I compute it via a Bayesian technique. Now what? You say, why is this an issue? Well, it's a huge issue. Because, let me just go to the next slide. If you are somebody who wants to understand about what to impact, what, you know, if you want to have an intervention strategy, and you've got one model that says this one is the best set of factors, and the other one says another set of factors, how do you, in a world with constrained resources, choose which intervention strategy is going to work? It's a very, very difficult problem. And now I'll just go to this, this diagram. It's okay, I'm getting into it. This diagram here, these were all our covariates, and these are the top 100 models. If you see a black column, it means that that variable, so if I go to depression here, it was in every single one. Okay? So if I go and you can figure out which are the most probable models. One of the things that came out of the study was that the location of the centre 3, was in every single one of the top models, and yet in their initial analysis it got a p-value of 0.92, so it wasn't even considered as, and that's because there's a lot of noisy other things going on, and it's only until you start to control for all those other things that you. But actually, the good news is here that the reason that this is interesting is that that means, well, you know, centre 3 is nothing about the centre, but there's obviously a proxy for something else going on, and so that would be open for further areas of investigation. Okay, and unfortunately, with more data and more methods, more research and degrees of freedom, irreproducibility will increase. We will see increases in reproducibility if we continue to do research the same way that we've always done it. Okay? So lessons learned is to be or not to be, that is the question. I'd try not to if you can. If you must, be aware of the limitations, okay? Because p-value is just simply the wrong conditional probability. We should, actually what I skipped over was there was a slide put out by the American Statistical Association. They said basically don't use it. Do not use it. And yet we continue to teach it. And I must say, we, I mean statisticians, it's our fault. I mean, we should be banning it, really. All models are wrong, but some are really useful. Combinations, we get much better predictions from combinations of models than from single models, okay? This is where the Bayesian stuff comes in a lot. Prediction is pretty easy. Inference, understanding the causes is very hard. Okay, so we've still a long way to go until we can take large data sets and give you great predictions, because different models with entirely different factors lead to the same prediction. That is not our issue. Our issue is how do we make meaningful inference so that policy can be developed in order to target these issues. Always perform multiple analysis of the data. That's what we did. That's what we ended up doing in this paper. We did not just one Bayesian technique, we did lots of Bayesian techniques, we did lots of frequentist techniques, and we showed how the results changed. And it's important because that gives you a sense of, it's not a bad thing to have the results change depending upon the analysis, but you need to be frank and open about what it actually is. And learn to embrace uncertainty. If we aim for reproducible research, then we need to quantify all aspects of uncertainty. And I like this, this was Brian Cox, he's a particle physicist. It says Brian, it's actually not, he has a right brain. He says science is not a collection of absolute truths. We're delighted when we're wrong. Well, I'm not sure that that's exactly right. But because it means we've learned something. I think that the scientific way of thinking is the road to better politics. The value in science is embracing that. So we've got to stop moving away from ambit claims that X leads to Y. And in order to do it, I think we have to also move away from the traditional statistical approaches into more newer methods such as the Bayesian ones. So I'm very grateful I've been able to give you this talk at the Bayesian Breakfast.
Very entertaining. It's great. And I think I do understand quite a bit of it, but I still thank God for mathematicians. So any questions for Sally around that? How many people use p-value as their main measure? Are you going to change?
Well, not until journal editors change, I suspect.
Yeah, I mean, that was the question I was going to ask you, because I mean, how do we handle that? So
psychology has taken an interesting route. The Journal of Applied Psychology, JAP, has actually come out and said it's not going to use p-values anymore, it's just going to use descriptive statistics, essentially. I'm not even sure that that's the right answer, because I'm not sure that that gets around the problem. But I think it's interesting to note that the problem is that the stats community has to communicate all this more effectively to the applied world. It's interesting to note that 30 years ago, most stats methodology papers, so people who come up with new techniques to do things, were frequentist, and 10% were Bayesian, and now it's about 90% Bayesian. But in all our articles, in all our top stats journals of World Statistical Society, Journal of the American Statistical Association, they're 90% Bayesian. We typically do not use the frequentist statistics at all. And so we haven't communicated that, and that needs to happen.
All the grad students, there was a saying going around that Bayesian is the next thing in statistics for the last 200 years.
Yes.
So do we think that we really kind of got to the watershed part where we are turning a corner? I know in psychology where I am, we see more and more Bayesian statistics actually in our mainstream journals, but it's still a drop in the water compared to the null hypothesis testing. So,
yeah, look, I suppose it's because the null hypothesis testing is a sort of cookbook recipe style. Anybody can do it. The reason that Bayesian statistics was around ages before frequentist statistics, but never got a wriggle along, was because it actually, I haven't put it on the slide, but it involves performing multi-dimensional integrations, very high-dimensional integration, which simply was not possible before we had the computer power that we do now. So that's why it didn't take off. It couldn't take off until we had computing power to do that. And also, having said that, because you do need that computing power to do it, it typically involves working with an expert. There's not sort of drop-down menus that you can easily use Bayesian statistics. We're working on it, developing software that makes it more readily available. But yeah, I think it's harder for an applied researcher. You can't just download a package of Bayesian software and run it. So.
There.
Very interesting, thank you. So I do clinical trials,
yes.
And so in the clinical trials world, the way that people have dealt with their research and degrees of freedom is to pre-specify analyses.
Yes, and that's a good way of doing it.
But that's kind of the opposite to what you said about the multiple analyses. So I wondered if you could comment on that from the Bayesian point of view.
So the reason to do multiple analyses typically stems from the fact that if you've got observational data, and you're free to choose, you would choose the analysis that suits you. However, if you say up front, this is the analysis I'm going to use before I've even got the data, then that's a guard against using a particular analysis. So I think that that is actually a very good way to go. But it's interesting to note that even so, a lot of things can't get replicated, even when you do all the right things. And I suspect a lot of that is to do with p-values.
So I was wondering if you could recommend maybe some resources for learning how to run Bayesian analysis.
Yeah, I would love to, and I think it's all going to be available at Sydney Uni very shortly, but not at the moment. So I suppose there's a few textbooks out that I think that do it well. There's I know I can see it. It's got puppy dogs on the front, and it's got Bayesian something in it.
Andy Fields has a running Bayesian with R.
Yeah, so there's lots of, so if you're comfortable in R, the best Bayesian sort of run stuff to do is a package called Stan. Stan can run from R, it can run from Python, it can run from MATLAB, and it does all what I haven't touched on, which is MCMC, it does all the MCMC for me. So,
we can send resource rounds.
Yeah, so, yes.
Jack will send it to
Yeah, I will. I think actually, and what we are doing at Sydney Uni is because we've actually recognised that it's something that we really need to do, sort of together with Tim and other people around the university, we're launching a PhD program in data science, and one of the main parts of that program will be training researchers in Bayesian statistics.
I mean, what we want to be able to do with that is actually have a program that includes people that come from data science and people in biological science and medicine. And so if you're in the more medical side or health side, then you're going to come and actually do a short course in Bayesian, so you can do that. So we want to be able to kind of balance everybody out in a way.
Yeah.
That people that are in the data science can come and actually learn a bit about the health side as well. So we start to build that program.
Yeah, and and we probably will be putting out just next year the Data Science Centre and Bayesian course. So I'll send updates on when that will be running.
Any other question there? We just use the mic, we just record it so we can show it.
Okay, that's right. Do you think the sort of added complexity of Bayesian analysis kind of opens the door for maybe even more manipulation of effect sizes?
Well, we don't actually have to worry about effect sizes in Bayesian analysis. So the flexibility of Bayesian models is, I think, excellent. One of the things that Bayesian models are often criticised for is that you do have this flexibility, particularly this thing called prior distribution, right? But the great thing about a prior distribution is it makes you absolutely explicit about what you're assuming, and so the person who's reading it can see what you're assuming. You can then have a mechanism where, well, if my prior assumptions are incorrect, how's that going to change my inference? Whereas, of course, there are implicit assumptions in all the frequentist tests that you do. Or when you do p-values, when you do, how many of you check whether asymptotic normality of your coefficients, F-sampling distribution of your coefficients is there? How many have heard of asymptotic normality of your sampling distribution? Okay, so they are built into every single hypothesis test and p-value that you do, and yet nobody worries about those assumptions because they're not explicit. I mean, how many? So there's a workaround to the asymptotic normality. You can do finite sample tests. So how many of you do regularly perform finite sample tests? So being explicit about what you assume is a good thing.
Any other questions? I'll go there then to the back. Yes.
So my disclaimer is that I'm not a statistician or a mathematics person. I work in biology, and as in biology there is just so much uncertainty. We look at one particular thing and we just do the p-values or whatever testing we do. So is there any way, like I'm just like a general answer from you about the uncertainty component.
Yeah.
How do we measure that, or how do we put it in our equations?
Yeah. Okay, so what you basically do, it's a very good question, and it is actually one of the best things about Bayesian statistics, is modelling joint uncertainty. So you don't do a little bit and get a p-value and then another little bit, you put it all together. Now the way you get the joint uncertainty is because you put priors over the things that you're interested in, you get some data, and then you churn the Bayesian machine and you get a posterior. And that posterior enables you to jointly model the uncertainty of all the variables. We have a similar problem in geology where there's just so many things that are uncertain. But in order to do that, people have to be comfortable with uncertainty. So the reason that they do these things one at a time is they want to get published, and they're not going to get published if they say, well, actually, I'm really unsure. This is what I got. It could have been anywhere, but yet we must be willing to embrace that uncertainty. So yes, absolutely, I'd say one of the best benefits of Bayesian is the ability to deal with joint uncertainty.
So, one more question with that as well.
Do you think that there's a place for frequentist statistics?
Yeah, I do actually. I mean, I know I give a lot of rubbish, but that's because I'm sort of dyslexic a bit. Yeah, when you're doing simple linear regression, you've got lots of observations. Absolutely. It's easy, it's quick. You may as well do it, and certainly some of the Bayesian statistics, when they set prior distributions, actually use a lot of frequentist statistics to think about what is a sensible prior. So absolutely, I am a die-hard Bayesian, but there of course is a place for frequentist statistics.
Last question. I don't really have to dash off, Sally, whether you can stay for a minute.
Yeah, no, I don't. I've got another meeting at 9.
That's great. So we've got breakfast outside. Last question.
I just wanted to pick up on your point about the effect sizes, because that's something that I don't find a problem. I find it useful and informative. So is there sort of an equivalent?
Well, you could. It's just so the reason that you have effect sizes is that you need a certain power of your test. So you've got to calculate how many observations, if I understand your question correctly, you need in order for your test to have a certain power. But that's normally what is required when you send it out for reviews and things like that. So you could hypothetically do that with a Bayesian thing. I mean, what happens with a Bayesian posterior probability? It automatically reflects the sample size. It'll be broader for less samples and narrower for more samples. So, but I suppose what I'm trying to say, there's no sort of cookbook recipe for saying if I do follow these set of rules, then this is the outcome I'm going to get, which is clearly one of the reasons it hasn't been picked up, I think, a lot.
Okay, great. Well, thanks very much, Sally. I certainly learned a lot, I think. I just have to dwell on it and maybe watch the video again. So maybe just thank Sally again. And, I encourage you to... Jack, is everybody kind of automatically a member if they've attended this or not? Or they have to register? They have to register still within the network?
Yes.
Right, so what was the address again? It's DHIN. So DHIN.net.au is the link to the network. So if you join with that, then you'll get all the updates on activities that are happening as well. And as we start to look at rolling the PhD program out and other things like that, you'll get that information. So you'll be hearing a lot more from us.
And I'll send you those materials, and we have a link going about where you might be able to access papers and books and anything else that you'd like to know about the series of lectures.
So we'll have a recording of this available on the website that Jack's made. So I should have said this is Jack Wells, and introduced at the beginning, Jack. So Jack is the actual coordinator of the network, and Jack's actually working across a number of our multidisciplinary centres, kind of identify where we've got kind of people working within digital health, both across the statistics, maths, data science, and biological sciences and medicine. Anyway, thank you very much, and there's still plenty of breakfast out there, I think, so help yourselves, and Sally's here to answer questions for at least a little while.